So today, I wanted to continue our conversation that we started on Wednesday, um, and sort of do a little bit, maybe better of a job, because I had a conversation about all the stuff that we've done, but it was literally that. It was a conversation with no visual support. And I realized after the fact that that's really hard to keep track of. So I wanted to do it again with a little bit of visual support. And this is good preparation because even though you just took a test yesterday, the final exam is really right around the corner, right? So it should already be time in your brain to start gearing up to prepare for the final exam, okay? It's cumulative, right? So everything that we've talked about from the beginning of the semester until now, and the stuff that we're going to add on in the next week and a half, right, is going to be on the final. So it is not too early to start preparing for that, right? And especially now that you have this whole semester perspective about what I'm trying to achieve with you guys and this attention to meaning and how does calculus work, right? What are the ideas behind it? Hopefully now when you go back and you look at the beginning of the semester, you can bring that perspective and that lens to your studying and get more out of it than maybe you did at the first glance, right? So that's my hope for you. One other thing. So something I did in office hours that I hadn't done in class was coach people on how to study, right? Which sounds a little silly because at this stage in your career, you've been through at least 12 years of school, right? So you probably have your own methods. But something I've noticed throughout the years is that for whatever reason, there tends to be a mental block about your study skills for school that don't translate to your study skills for math. Okay, so whatever it is that you do to study for your psychology class or your sociology class or your chemistry class, you can apply those skills to your math class, right? Because this math class is about ideas, okay? And so, if you like to make tables of information or concept maps to show how they're related, right? And how do you get from this idea to this idea? What's the connection between them? Those kinds of things apply here, okay? So using those study strategies to prepare for the final would be an excellent idea. Mm-hmm.
The hard thing about that is I could give myself practice problems, but I don't know if I'm doing it right or not.
Right.
There needs to be some system to do practice problems where it says no, you were wrong.
Okay. Well, so definitely as far as being able to check your work, what I'll do is I'll go back and I'll post blank quizzes so that you can try to do the quizzes again. And then the solutions are already online, so you'll be able to check your work that way. For the My Math Lab, you can go back and do review mode for all of the assignments, and it'll tell you whether or not you got the questions right or wrong. But if there's other things where you go back and you are looking at problems and you want to know, did I do this right? That's when you talk to me, right? Take a picture of your answer and send it to me in an email, and I'll let you know if we should have a face-to-face conversation, or if it's as simple as, yes, you did that right. Then I'm happy to do that as well. Okay, so there's no reason ever for you guys to be studying and wonder, am I doing this right? That's what I'm here for, right? I'm here to support you. So, and Mark as well, and Marissa Bell as well. So please take advantage of us. Yes.
I was trying to study for this last test through my math lab.
Mm-hmm.
I found it, I wanted to use the study plan, but I found it difficult because we didn't really go in order of the book chapters, and I wasn't exactly sure of which chapters we pulled from, and I tried
Yeah.
and so it would be beneficial for me, I think, to know where the information is
Mm-hmm.
in our book.
Okay.
So that we can go on to the study plan, and they've got practice tests and problems that you can do.
Okay.
And you can work through them, and it'll help you. And
Right.
I find that really beneficial to kind of.
Okay. I can. It'll be Sunday before I have time to do anything. But I will make. Sorry, I know you asked me that before, and I just didn't have time to do it. So on Sunday, I'll put together a list of sections in the book. So the one thing to be cautious about when looking at the book is that for the stuff at the beginning of the semester, right, we approached this in a sort of non-traditional way so that it could really develop a meaningful calculus, right? So there's not going to be perfect alignment between what we've done to really focus on meanings versus what a traditional textbook is going to do, which, even though they try to convey meanings, right, it's really, when you boil it down and look at most of the problems, it can be very procedural. Okay, so just keep your thinking brain on while you're doing some of the procedural problems, and ask yourself questions like, why am I doing what I'm doing? Why does it make sense to take a derivative here? Am I looking for a rate of change? Am I looking for an accumulation? What does this represent if I plug in this number? Is this a value? Is this a function? What is it telling me? If I were to graph it, what do the points on the graph represent? What's the behavior? There's tons of questions that you can ask yourself given any very procedural problem to do, right? But then you can make it more meaningful by asking yourself these questions, okay? Okay, cool. So let's get into it. So in the spirit of review, this is sort of, I don't know if you caught that. Did you catch that? Right? So we've done two processes, right? Accumulation from rate of change and rate of change from accumulation. Those are the two processes that we've done this semester. And the way that we went about doing it was to start with an exact rate of change, build an approximate rate of change function, and that involves this whole process of partitioning the x-axis, defining a left of x function, and then creating a piecewise step function that approximates the rate of change. Use those constant rates of change to develop an approximate accumulation function that's piecewise linear, right? The power behind constant rate of change. And then let the size of the intervals get really small, so our approximate accumulation essentially becomes our exact accumulation. And what we did was we introduced the summation notation so that we could keep track of all of that. And then once we let this process happen of letting the delta x get really small, because nobody wants to count up, thousands of delta x intervals, when we get delta x really small, then we introduced this integral notation to represent the exact accumulation, okay? And then we went in reverse, right? So we did that process, but then we went in reverse. So we started with an exact accumulation function, and we, again, divided up the x-axis into delta x intervals. We computed the average rate of change over each of those intervals to create a piecewise linear function. Now, by finding the average rate of change over all of the intervals, we were really finding the values for this piece, this step function for the rate of changes. And then again, letting delta x get really small, that gives us an exact rate of change function. Okay, so that was the process that we went through to go from accumulation to exact rate of change. Okay, so you might ask yourself, well, where did we find these exact accumulation functions? How do we come up with an accumulation function? Where do they come from? Can you think of an accumulation function that we've talked about? An example of one? Area? Area of a square? Holy cow. Check this out. That was my first example. Okay, so yeah, area of a square is an example of an accumulation function, okay? But the point is, accumulation functions come from everywhere, right? Most of the functions that you've ever talked about in your mathematical career have been about accumulation, right? Because you input some value, a side length, a radius, or whatever, and you output some total amount of area or distance or time, whatever it is, right? So pretty much every function that you've ever talked about before coming to calculus was an accumulation function, okay? They come from everywhere. So area is an accumulation function. And so we're used to thinking about it as, area of a square is x squared if the side length is x, okay? But now we've developed the tools to talk about this in terms of accumulation, in the sense that I can think about, while this animation goes, think about how the area is accumulating as x grows. So now, rather than just thinking about a fixed square, right, I can now visualize a dynamic situation where things are changing, and I can talk about that now, okay? And so that's what this second area formula helps us to do. It helps us to see the process, right? The process of accumulation of area, okay? What do we call that form? So the first equation is in closed form. The second is in open form. And again, so the first equation is useful, right, for just getting quick and dirty answers, okay? But the second equation actually helps us to see the process. Adam? Okay. All right. So just for kicks and giggles, here's another example, right? So a volume of a sphere. The difference between what you've done before calculus and now is that before you would talk about the volume of a sphere, right? Like you've got a basketball or whatever, right? And then you can just talk about it, okay? Well, now we can talk about a situation in which we have a spherical object that changes, right? It could either be growing or it could be shrinking, but it's changing. And we now have the ability to talk about how it's changing, right? How is the volume accumulating or shrinking, right? We can talk about these things now. That's the power of calculus. So if you ever hear somebody say, or if somebody asks you, what is the study of calculus? Tell them it's the study of change, okay? Because we can talk about dynamic situations, okay? So once again, we have a closed form formula for volume, okay, and an open form, okay? And again, this formula helps us to think about the process of accumulating little bits of volume, right? So a rate times a little bit of time will give us a little bit of volume. And we add all of those up to accumulate the volume, okay? So any function that gives the exact amount of one quantity as a function of another quantity is an exact accumulation function, and therefore can be represented as an integral of its exact rate of change function. Okay. It's a long sentence. Do you need a second to digest it? We good? Okay. So this is just what I was saying before. You've had years of experience with accumulation functions that are in closed form, and now we have the ability to think about accumulation functions in open form as an integral of the rate of change. Okay, so at the very beginning of the semester, given an accumulation function, we went through this whole process of building up how to get to, well, I guess that wasn't the first thing we did. We went the other way first. But at this point now, we've talked about how to go from accumulation to rate. So at first we didn't know how to do that, but now we do, right? So we've worked on all of these mastery rules. But of course, where did those come from? The definition, right? The definition of the derivative. So now we do know how to find the rate given the accumulation, okay? And so that process, the way that we figured that out was taking derivatives, right? This process of differentiation, okay? So this is a repeat slide from Wednesday, but it was a good one. So we're going to do it one more time, okay? So suppose that f and g are functions. If g is the derivative of f, meaning, right, because just saying g is the derivative of f, if you say that to somebody in a different calculus class, chances are they don't have all of these ideas in their head about rate of change. So the real meaning of that saying is saying g is f's rate of change function, okay? Then we call f an antiderivative of g, okay? So we have our functions f, the derivative of f, But then if you go backwards, right, from the rate of change to the accumulation, then we're getting the antiderivative. Okay, so this is just a naming convention. Okay. So again, this completes our cycle, right? So we can go from accumulation to rate of change, or from rate of change to accumulation. Full circle. Okay. So every accumulation function is an antiderivative of its rate of change function. Okay. And the thing to highlight on this page, of course, is, what is this, like an indefinite article or something in grammar, right? So it doesn't say every accumulation function is the antiderivative. It says every accumulation function is an antiderivative, okay? In comparison to how, if you have an accumulation function, right, there's only one derivative function corresponding to it, only one rate of change. But when you go in reverse, you introduce more possibilities, okay? So every rate of change function has more than one antiderivative. And we can see that through this conversation. So if I have x as my rate of change function, then an antiderivative of that is x squared over 2, because the derivative of x squared over 2 is x, right? But if I were to add the constant 1 to x squared over 2, well, that still is an antiderivative of x, because the derivative of x squared over 2 plus 1 is still x. And likewise, if I add 2, or if I add any constant, okay? So if I add any constant to x squared over 2, the derivative will still be x, okay? So all of these are antiderivatives, but if I want to represent sort of an arbitrary antiderivative, okay, then it's conventional to use this plus c, okay? So, okay. So here's the thing, right? So all antiderivatives of a function differ by at most a constant, right? That's what this is saying. So, question. Do you have a visual image in your head right now? I'm seeing a couple of people nodding. So I have words on a screen right now, okay? What I'm asking is, do you have a picture in your brain of what this means? No picture? Some people have pictures, some people have no pictures. So what could a picture look like? Is anybody who has a picture brave enough to share? Rochelle?
If you create an antiderivative of a rate of change, let's say it's kind of like a regular
Some curve. Okay, like, okay.
Sure. A constant would move it up or down, and without that constant, it could take up any point.
That's an excellent visual image. So let's share that with the class. Okay? So, not this one. Okay. So here, what I have is a little bit complicated looking at first, but shouldn't be too intimidating because we've worked so hard, right? So what is this thing that I've highlighted? A rate of change function, right? And so then when I look at this whole thing, what is that representing? An accumulation function, right? And so what I can do is, so this represents an accumulation function, and in terms of the language that we've just discussed, right, it is an antiderivative of the rate of change function u cosine of u, okay? Or if you want to use x's, you could use x's. So it's an antiderivative of x cosine x, okay? Now, I'm going to change what the value of a can be using my slider, okay? And so here's what happens. So currently, this is an image of the accumulation when a is -5. So starting to accumulate from -5, okay? Now if I change that value, then this graph moves up and down, right? So we're going to talk more deeply about why this works. But one thing that I'd really like you guys to think about that I'm not sure if I fully conveyed this well enough before is when you have a rate of change function, so this function here, it tells you about the behavior of your accumulation function, right? It tells you how is it decreasing and increasing and decreasing. Is it doing it in a concave up fashion? Is it doing it in a concave down fashion? And how is it doing it, right? So it gives you behavioral information. It doesn't give you information about the value of the accumulation, okay? And so that's where we get this leniency in moving it up or down, right? It could be up here, it could be down here, because where the accumulation is located is talking about the value of the accumulation. But what happens between these 2 points, the behavior, that is what is determined by the rate of change, okay? And so that's why no matter where the accumulation starts, the rest of the graph still has the same behavior, okay? So hopefully you have this image in your brain now of the same behavior of a graph, but then like infinitely many copies of it up and down, right? Shifted up or down, okay? So that's an image to have in your brain when I say that, sorry, now we have to wait for all of these things. When I say that, it's coming, all antiderivatives of a function differ by at most a constant. So you've got these like infinitely many accumulation graphs that are translations up and down of each other. And if you look at the difference between any of them, it's just a constant, right? I shifted this one up by 2 or down by 5. And so the difference between them is, 5. Okay? Okay. So if f is an antiderivative of little f, then it is customary to write big F of x equals the integral of little f of x dx. Okay? So this is just notational customs. Okay? And if big F is an antiderivative of little f, then the integral of little f of x dx is equal to big F of x plus some constant. Okay? So again, this is just to give you like notational experience. It's conventional for people to use lowercase f to talk about the rate of change function, and then a capital F to talk about the corresponding antiderivative. Okay? And then C again is this placeholder for any constant that you want, right? Okay. An important thing to keep in mind, so here's an example of the types of questions you should be asking yourself when you're studying. What is represented on the left-hand side? What kind of thing is it? I'm hearing some, Shelley, what did you say? It's an accumulation function. In particular, it's a function, right? And on the right-hand side, is this a function? It better be. If the left-hand side is a function, then the right-hand side better be a function too, right? Because we're saying these two things are equal. So big F of x is an accumulation function, and C is a constant. You add a constant to a function, you still have a function, okay? So that's an example, right, of something that you can do to check yourself as you're working. Am I looking at a function or am I looking at a value? Okay? So here we go. So if we have a rate of change function R, then the accumulation function defined by R is big R, okay. What would big R be in open form? I heard some murmurs. Yeah, what are you going to say, Miranda, right? Yeah. What were you going to say? Okay. R of t dt. Cool. Okay. So this is how we get our accumulation function. Okay. And again, the reason that we use a t instead of an x inside the integral is because using this notational device, it's saying we're going to accumulate from a up until x, and x is our designated stopping point. So it's not representing changing things in this notation, right? It's just our stopping point. So we need something to keep track of what's going on in between. So we use t, okay? Okay, so where f of x, big F of x, is an antiderivative of r of x. Question?
Is the A at the bottom of the
Uh-huh.
is that what C is?
Ah, so that's where we're going. So we're about to figure out what c is, okay? So, all right, so we're gonna do this conceptually first, and then we'll do it algebraically so that you can see it too, okay? So let's imagine that we're dumping sand onto a scale, okay? And so, as you would imagine, right, you start with an empty scale, and then you start to dump your sand, okay? So on the left-hand side, I have a graph showing how, showing the rate of change of weight as a function of time, okay? And on the right-hand side, what is being represented? The accumulation of the weight of the sand on the scale, right, as a function of time. Okay? So, okay. Whoops. Too fast. So, okay. So let's think. So as I'm pouring sand, tell me what's happening. So the rate of change is positive to start with, right? But it's kind of a small positive value. And then the rate gets to be a bigger positive value. And so when you're comparing that to the right-hand graph, so you have a rate that's a small positive, right? So if you were to look at a little change in x, there's a very little change in y, versus over here where the rate of change is a bigger positive, so a little change, oh, I went too far. So this is around, what, 0.6? So around 0.6 over here. A little change in x will give you a bigger change in y, right? And then if I go to 1, right, then a little change in x at 1 will give me an even bigger change in y, okay? So that's how you can compare the rate of change to how the accumulation is changing, right? Because remember, rates tell you about the behavior. It tells you how is the accumulation changing, okay? So, all right, so initially I might, well, it would make sense to start measuring the weight at time is 0, right? Okay, now let's say that my scale's numbers only go up to, like, I don't know, 1. It's like a kitchen scale, okay? It's like 1 pound, all right? Now, but pretend that it won't break if you go past it. It's just that the numbers will only go up to 1. So you get to like 1 pound of sand on your kitchen scale, but you want to keep pouring more sand. But the numbers don't keep going. So you reset the scale, right? So I want to reset my scale so that now instead of counting the accumulation from 0, I'm going to start counting. Ooh. Oh no, what'd I do? Hold on, sorry. Why did it? What happened? Oh, that's all in one thing. I have a feeling this is going to show up on my teaching evaluations. She can't use technology. Okay. All right. So let's say we reset the scale when we get to 1 pound. And so now I want to keep track of the accumulation. Or sorry, not 1 pound. When I, I tricked myself. So we're going to reset our scale after 1 second of pouring, okay? So forget the 1 pound. Apparently we cut off at 2 pounds, okay? So, and then we're gonna reset our scale to 0, right? So the scale is holding 2 pounds, but we're gonna reset it to 0 and then keep track of the accumulation from there, okay? Does that make sense? Okay, so, but what does that look like? So what we've got here, right, is a way to keep track of accumulation from some A value to some ending value, right? So if I was starting originally, so this really isn't an A, this really is 0, right? This accumulation is starting at 0, and you can see that because at time 0, there's nothing there, right? 0 weight, okay? So currently we have this situation where we're keeping track of the accumulation from time is 0. But what I want is to keep track of the accumulation from time 2 seconds. So how could I write that? From 2 to x, right? So this would represent the accumulation starting at 2 and going to x. Now my goal is to somehow be able to figure out what this is using my function big F. Because notice that this is not big F, right? I've got a 2 down here and I've got a 0 down here. So these are different expressions. This equation is keeping track of accumulation from time 0. This equation is keeping track of accumulation from time 2. They are different functions, okay? So right now what I'm wanting to do is find a way to represent this using my function f, okay? So, well, let's think about it. So if I want the accumulation from time 2 to x, how could I get that if I can talk about the accumulation from 0 to some x value? So accumulation from So f of 2 is going to tell me what? So f of 2 will tell me the accumulation from 0 to 2, right? So f of 2 is whatever this value is. This is big F of 2, right? Ah, shoot. 2 seconds. Oh, I'm being really confused this morning. I'm so sorry, guys. So I was going from 1. That's okay. You know what I mean now. So 2 seconds is over here. So f of 2 is something over here, right? Some value like that. Okay, so then, so I could say, all right, well, let me consider, so if I have the accumulation from 0 to 2, and then x is somewhere over here, right? Then I want the accumulation from what do I want? I want the accumulation from 2 to x. So 2 is a bad choice because there's very little difference between 2 and this x value. The accumulation is very small, right? There's some like really little change in y there. Can you visualize it? Sorry. Okay. So if I want to figure out that change relative to this, right? I can say, okay, well, the accumulation from 2 to x is the same as if I had accumulated from 0 to x, but then take away the accumulation from 0 to 2, right? So if I think about the total accumulation from 0 to x and then remove the accumulation from 0 to 2, that'll just give me this leftover accumulation from 2 to x, okay? Now this thing in terms of big F is big F of x. And this thing in terms of F is big F of 2. Okay? So we've established this relationship where if I have the integral from some, so this generalizes, right? Nothing I've said is unique to the number 2. Do you agree? Nothing is special about 2. So I could replace 2 everywhere. And also nothing is special about 0. I can replace 0 everywhere. So from little c to x will be the same as the accumulation from some a to x. So let's put this back to being f of a again. So the accumulation from c to x is the accumulation from a to x minus the accumulation from a to c. Okay. So this is a general relationship between the open form accumulation and the closed form accumulation. Now notice if I rearrange this equation, I get that my accumulation function, my antiderivative, right, big F, is equal to the integral from c to x of the rate of change function plus big F of little c. And big F of little c is it's a constant, right? It's just a number. So rather than writing big F of c every time, mathematicians are lazy. Remember that, okay? We just write big C. Okay? That's actually a lie. Mathematicians aren't lazy. We just try. We try to be efficient. Okay. This is slightly bad notation because my big C looks a lot like my little c. So let me change this to like an A just so that we don't get confused. Okay. The big C and the little c were different. Okay. Problems with efficiency. Okay. So so this idea of, hey, we had accumulation from 0 to x and now I want to start from 2. This is an idea of resetting the scale, if you will, right? So that was this process that we just went through. So the total weight of the sand can be thought of in 2 parts. It's the total weight that's accumulated in the first c seconds, and then the weight accumulated after the reset, right? And then we rearranged to get this really nice relationship, okay? So, dang. How far do you want to get today? How are we feeling? Is this a good day?
Yeah.
This is good? Okay. So then let's just keep it going good, and we won't rush. We'll do, sorry, that means that you brought your computers for no good reason today. Well, we're going to do what I was planning on doing on Monday then, okay? So this reset idea. So what do I have here? I have a rate function, okay? And it, let's see, this rate, and thus the association begins way out to the left. Yes, okay, so let me graph the rate. So here's a rate function, right? And notice that this rate function, it keeps going forever, right? It goes way out to the left, okay? So when we talk about accumulation, we've kept our concentration pretty close to the origin, right? And that's been completely for the sake of ease, okay? It's easy to see it in a picture, okay? But you can keep track of accumulation starting anywhere, okay? Now, let's think about it for a second. If I start keeping track of accumulation somewhere, let's say I start keeping track of accumulation at 0.5, okay? Then what would I expect the value of my accumulation to be at 0.5? So if I start accumulating when x is 0.5, what should the accumulation be at 0.5? 0. Okay? Because you haven't had any any changes in x to allow for accumulation to add up, right? Okay, so, okay, yes, question.
If you were to see, it looks like you have a period of pi or something.
Okay.
But that, if we were to start like x equals 0 and then go a period of pi, that would technically be accumulation 0 for that whole point, even though we have all that movement.
Be very careful about how you're thinking about rate of change versus accumulation. So the period is actually closer to 2 pi, right? It, like this graph starts to repeat here. Like, so if I think of it as a quote starting point where my hand is, and then the next starting point of the cycle would be where it is now. So it's closer to 2 pi. But regardless of that, what I think you were thinking about was just from like 0 to pi, right? So over the course of 0 to pi, the rate of change is negative practically the whole time, right? There's only one x value where the rate of change is 0. So for the rest of the x values between 0 and pi, what is the accumulation function doing? Decreasing, right? So there's no way for a function to be decreasing over an entire period and end up back at its starting value, right? So be careful about the way you're thinking. However, what you did say would be true if you actually looked at a whole period, because you'd be accumulating and increasing, right, in this fashion for the first pi, and then you'd be decreasing in the exact same manner for the second part of the period, right? So if you look at the net accumulation, you'd be increasing in some fashion and then decreasing in the same fashion. So you would actually end up back at a net accumulation of 0. Okay, question?
I just, for a refresher,
Yes.
when the rate of change hits that 0, then goes back down, like in between 1 and 2.
Yeah.
That would be an inflection point, right?
That is an inflection point, absolutely. Because the rate of change goes from increasing to decreasing. So the corresponding changes in accumulation are like getting bigger and then smaller. Yeah, okay. Okay, so how would I write the corresponding accumulation function if I wanted to start accumulating at 0? 0.5. 0.5. So remember, I gave you the rate of change function. So I now want the accumulation function, where I start accumulating at 0.5. I'm seeing some of this. So here, from 0.5 to x of, yeah, that function, right? Okay. So something like this, right? So again, I have the apostrophes for the second window to make this graph. Okay, so we could graph this guy. Whoops. Whoa, what's going on? This guy. In the second window, okay? And keep track of the accumulation. Now, the way I want you to think about this is, so notice, right, the accumulation at 0.5 is 0, right? And then at 0.5, the rate was negative, so as you would expect, the accumulation decreases after that. Whoa. Why is it graphing what? Why is it graphing before 0.5? This is a really good question. This is a really important question. Okay, so this is sort of the catch to our development of calculus with meaning, right? Is that mathematics is ultimately an abstract field of study, okay? So we have developed meaning for having rate of change and accumulation, where when we look at this graph, we're thinking we're imagining that, okay, if I only consider the rate from 0.5 on, so that I can think about accumulation from 0.5 on, then that's all well and good, right? But remember what I said earlier today, is that the rate of change function tells you about the behavior of accumulation. So if I have a rate of change function whose domain is all real numbers, then it will tell me about the behavior of a corresponding antiderivative function, right, for all real numbers. Okay? Now, how you interpret the meaning of this graph to the left of 0.5, if you're thinking of this graph as an accumulation function, well, that gets weird, right? I don't know how to do that. Okay? But what I could say is, all right, well, now if I want to be able to think about this as an accumulation function, then where I'm keeping track of accumulation starting at 0.5, then I really am only going to think about the part of the graph that starts at 0.5 onward. Okay. Now, if I want to think about the accumulation not starting at 0.5, but instead starting at negative 0.5, does it look different? Does it look the same? It looks the same. Okay, let me pick a different number. Negative 1. Okay, now it looks a little bit different, right? So notice that now the accumulation at negative 1 is 0, right? And so if I'm thinking of this in terms of accumulation and using that meaning, then it makes sense for accumulation at negative 1 to be 0, and then use the information about the rate of change to figure out the behavior of the accumulation from there on out.
So it's going to set whatever your vote is as 0.
That's exactly what it'll do. Okay. So what your homework asks you to do, right? So today was all about making sure you understand the concepts and giving you ways to think about the meanings. What your homework is going to ask you to do is highly computational. Okay. So don't lose everything that we talked about today. But what your homework is going to ask you to do is things like this. So I gave you a rate of change function that looks like this. What function would be an antiderivative of this rate of change? You had to do that for today, and you'll have more practice on it this weekend. The difference between today's homework and the one for Monday is that you have to find values of C. That's the difference. Okay? So that's why I said paying attention to the difference between function and value is going to be really important in this weekend's homework. Okay? Nobody gave me an answer. What's an antiderivative of this function? Cosine of x to the 5th? Is that it? That'll work. Cosine to the 5th of x. So that works. Okay?